This is 8.1.5 nuclear radius. So in today's lesson, we're going to look at different methods of calculating or estimating the nuclear radius. And we're going to look at the limitations of some of them. So the first method is to fire an alpha particle at a larger nucleus. So we'll draw our alpha particle with its 2 protons and 2 neutrons. So that's 4 to He. And that goes towards a larger nucleus. And this is of some arbitrary element. Now, the nucleus has some radius that we're going to call R, capital R. And the separation between the helium nucleus and this larger nucleus, we'll label that as small r. Now, when this helium nucleus gets close to the larger nucleus, it's going to slow down. And at some point it's going to stop, and it might even turn back around and go back. So the kinetic energy of the helium nucleus does work against the electric field of the larger nucleus because they're both positive. So if we consider that, we've got Ek turns into Ep. And the electric potential is given by Q alpha times by Qx over 4 pi epsilon naught r. So Q alpha times by Qx over 4 pi epsilon naught r. So if we rearrange this, we can get a value for r. Now, we make the assumption that the helium nucleus gets so incredibly close that it's pretty much touching the nucleus. And because alpha is much, much smaller than the nucleus, the extra radius added on by the alpha particle is small, that it becomes almost negligible. Not quite, almost. So rearranging this, we've got R equals to Q alpha times by Qx over 4 pi epsilon naught Ek. So with this, we assume alpha particle is almost touching the nucleus. So if I draw that, there's your alpha particle, and I'll leave a very small separation. Now, even with that assumption, this little r that we calculated is still larger than the actual nuclear radius. So the actual nuclear radius, which is r, is less than r, little r. So the story here is that kinetic energy of alpha particle did work against the electric field of nucleus X so EK turned into EP. And so this gives an estimate for the nuclear radius but it's an overestimate. Okay. Next, we'll look at the nuclear radius using electron diffraction. So, we start with a filament. When the filament gets hot, it starts to emit electrons. Then we pass it through a small tube, which is electrically charged, so the electrons accelerate towards that tube. So it's at some potential difference, V volts. So the potential difference accelerates the electrons, where the energy is equal to QV. So these electrons then strike a small sample. So that's a thin sample. And then at the end they strike a screen. So as it's passing through the thin sample, the nuclei start to behave like slits. And so diffraction occurs because electrons have wave-particle duality. And on the other end, you get single-slit diffraction pattern. So when that happens, we get some electrons which go at some angle, theta. So that's, for example, your second, your third order. So electron diffracted by nucleus. Or by nuclei, because there's multiple of them. So first thing, we need to find the de Broglie wavelength. Of our electrons. So lambda equals to h over mv. Next, for diffraction to occur, that separation, r, the nuclear radius, has to be roughly equal to the wavelength of the electrons. So the slits have to be roughly the same as the wavelength. It doesn't mean identical, but they're in the same order of magnitude. So nuclei behave like slits. So R is roughly equal to lambda for diffraction to occur. Now again, this isn't the most precise method. So a more precise method then is with this equation. R is equal to 0.61 lambda all over sine theta. Next, we're going to move on to the electron gun equation. So the electron gun, basically, as electrons are emitted from the filament that we drew before, if electrons are just about being emitted, they're not leaving the filament with very much energy. And they're also moving in all directions. If you place a charged metal plate or a charged metal tube in front of it, the electrons then do work, or work is done on the electrons rather, and it accelerates the electrons towards that metal plate. So work is done on the electrons, and the electrons gain some kinetic energy. So all we do is we say that the energy gained is QV, and that energy gained becomes the kinetic energy of the electrons. So that's the electron gun equation. That QV is equal to a half mv squared. So this is the energy gained from E field is equal to the kinetic energy. Now usually in waves when we talk about diffraction, we tend to use monochromatic light. So monochromatic light means that they have the same frequency. If all the photons have the same frequency, then all the photons have the same energy by E equals to hf. In this situation, we want the electrons to have the same wavelength. So if we want the electrons to have the same wavelength, we need to use monoenergetic electrons. So all electrons should have the same kinetic energy. If they have the same kinetic energy, they have the same velocity. If they have the same velocity, they have the same de Broglie wavelength. So for electron diffraction, use monoenergetic beam of electrons. So monoenergetic means that they have the same velocity, which in turn means same wavelength. So that once they diffract, we end up with thin rings that are easy to measure, rather than having spread out rings that are difficult to then measure. So we want to make sure that our results have a good resolution. If we have lots of different wavelengths passing through the slits or through the nuclei, then you're going to get rings on the other end that are kind of thick and blurred together. So it becomes difficult to determine which part of the ring corresponds to what energy and what wavelength. So if we sketch what happens, if that passes through, you get some angle, and it forms a ring on the screen, right? Because it's in, if you think about it in 2 dimensions, some of the electrons diffract upwards at that angle, some to the left, some to the right, and all around. So even though that angle is still the same, you can rotate that around when you think about it in 3 dimensions. So it creates a 2-dimensional image on a screen, not a 1-dimensional image. So if you think about it as a 1-dimensional image, you think of the maxima minima. When you think of 2 dimensions, it creates rings on the screen instead. So in the center, you'll have a bright spot there, directly in the middle. And then you'll have rings surrounding it. Yeah? So this is monoenergetic. And if you don't have monoenergetic, then your rings will basically become thick and blurry. Non-monoenergetic. So there are lots of different angles. Which makes it difficult to measure. Now there's another method, again, to estimate the nuclear radius, and this method tends to work really, really well. So when we normally talk about the nucleons, you think about it in terms of spheres. Instead of spheres, let's estimate that they're cubes, or assume that they're cubes. Okay? At very, very small volumes, the area of the cube and the sphere are almost the same. So they roughly occupy the same volume. So radius and nucleon number. So let's assume that nucleons occupy space like a cube. So if we had a cube, there's our cube. If we had an A number of nucleons, if we have an A number of nucleons, they arrange themselves to form a larger cube. So here's our larger cube. So let's think about this. If one of these cubes had a diameter d, which means it's the same on all sides, then each cube has a volume V equals to d cubed. The total volume, so I'll call this V1, the total volume for the entire nucleus with a number of nucleons is just A times the volume of one cube. So V total is equal to A times by the volume of one cube, which is A times D cubed. That gives us the total volume. Now, the total volume also depends on the diameter of the nucleus itself. So we'll label this diameter as capital D. So V total is also equal to D cubed. So now we can put those all together. So we say that D cubed is equal to A times little d cubed. So the diameter of the large nucleus cubed is equal to the number of nucleons times by the diameter cubed per nucleon. Now we can get from there to the diameter of the actual nucleus by cube rooting it. So D is equal to little d times by A to the 1 over 3. And then we know that radius is half of diameter. So if we divide both sides by 2, we get the total radius of the nucleus. So R, the radius for one nucleon, we call that R naught, a to the 1/3. So this equation will calculate the nuclear radius. So we'll write that here. R is the nuclear radius in meters. R0 is the radius per nucleon, which is equal to 1.05 femtometers. And A is the number of nucleons. Right. Start a new page. Now we'll look at using data to find the equation. So the nuclear radius, we can find that using electron diffraction. You can find the nucleon number by looking at the periodic table, and then we make an assumption. So find R using electron diffraction. Find A from the periodic table. Then we assume that R is equal to K A to the power of N. Similar to what we did in thermal physics, we made an assumption and then we started to log it and graph it. So, we can see from this then that K, since I've already told you the equation, you expect K to be equal to 1.05 femtometers. Yeah? And N, you're expecting that to be a third. So when you gather the data, you log both sides. So you've got ln R equals to ln Ka to the N. The K and the A will split and be two logs added together. So ln R is equal to ln K plus ln A to the N. The N will just come outside. So ln R is equal to ln K plus N ln A. So you do this for a few different elements or a few different isotopes where A is different, the nuclear number is different. And after you've done this several times, you get some data. You plot it into a table so you can see all your different data have been logged. Then you plot a graph. So I do Y equals to mx plus C. And then they get a graph that looks like this. So you've got ln R, ln A. They get some values, plot a line. And they found that the gradient was equal to a third. The gradient, which is N, equals to a third. And then they found the intercept, which is here, C That's equal to ln k. And ln k is found to be ln 1.05 times 10 to the minus 15. If you could just put that into a calculator and give us a value.
Minus 34.5.
Okay. So minus 34.5. So we didn't have to read like very small numbers for this. Each of those numbers was something rather large. So you could use the graph to calculate it. Okay, and final thing for today's lesson is nuclear density. So we start by assuming that R0 is equal to 1.05 femtometers and that the mass of the proton is equal to 1.67 times 10 to the minus 27 kilograms. Then we can assume two things, that the nucleus is either a sphere or it's a cube. So assume nucleus is A, a sphere, B, a cube, the volume of the sphere is equal to 4 over 3 pi r cubed. Now, because we're doing it for the nucleus, I'm going to change that R to a capital R. And for the cube, V cube, we do the radius times 2, that gives the diameter, then you cube the diameter to get the volume. So it's going to be 2 capital R, all cubed. Now, if we did that, we get 2 cubed. 2 times 2 is 4. Times by 2 again, 8. So that will give us 8r cubed. 4 over 3 times by pi is as a number, decimal, so put it into a calculator.
It's 4.2.
Okay, so 4.2. So if we model it as a sphere, we get a less volume than if we modeled it as a cube. Okay. At this point, though, we have enough information about the nuclear radius that from this point we can model it as a sphere rather than a cube. But you might have instances where a question asks you to model it as a cube. Okay. So, then we know that density, rho is equal to mass over volume. So, for a sphere, we do the density is equal to, the mass is just the mass of the proton multiplied by the number of nucleons. So A times the mass of a proton, that gives us the total mass. And then the volume, which is what we had above, 4 over 3 pi r cubed. And then the 3 goes above. So this is sphere. For the cube, we do the same thing again. So rho equals to, the total mass is just A times the mass of a proton. And then we divide that by the volume, which is 8r cubed. And I'm going to put one little note below because there is a point in here that could lead to a misunderstanding if you were to check these notes later on because of the use of A. So note, A here is the nucleon number. Because the moment where we start using things like volume, it becomes very easy for your brain to steer away from A being a nucleon number and start thinking of it as an area or a surface area. So we just make a little note at the bottom to make sure that when you glance over these notes at a later date, that you don't get confused as to what A stands for in this situation. Yeah, it's just a little reminder to yourself. And that's the end of 8.1.5.